I'm Ollie Hanton and I'm introducing our project FabricatINK, the personal fabrication of bespoke displays using electronic ink from upcycled e-readers. We'll start with a bit of interactivity. Even though this is a recorded video, could you raise your hand in front of the camera if you own an e-reader? In practices of this talk, about half the audience did. I'll ask you to raise your hands again if you understand how e-ink works. In practices, less than a quarter knew. So let's take a closer look. Here's an image we took using a microscope of e-ink microcapsules within an e-reader. Each microcapsule is 40 microns or 4/100ths of a millimetre across and has the ability to change colour from black to white with grayscale in between. For context, the square shown is the approximate size of a monitor's pixel. We can see that there are multiple microcapsules per pixel, giving the potential for high-resolution colour change displays. So how do these microcapsules work? If we take a high-level dissection of e-readers, we see that there are multiple layers with the e-ink being sandwiched between electrodes. This is a side view of the layered structures of e-ink microcapsules. Each capsule is formed of silicon oil with suspended charged particles of white titanium dioxide and black carbon black. When layered between electrodes, an electric charge between the electrodes moves the particles within the microcapsules to change the colour that can be viewed from white to black or black to white. Interestingly, these particles can be deposited and adhered like a traditional ink or other active material alongside fabricated electrodes. Since the display works through movement of particles, it has unique display properties. E-ink displays are truly bistable, that is to say they retain their state without power. They're also high contrast, low power, robust and formed of cheap materials. So if e-ink is as versatile as an ink, why is it limited to rectangular pre-manufactured display shapes? In this project, we show that e-ink can be formed into irregularly shaped bespoke display pieces using tools and materials found in a hackspace. We demonstrate that e-ink can be manipulated like an ink and is an optimal material for personal display fabrication. In this process, we produce the demonstrators shown of sample applications for which e-ink would be well suited. Related work in display fabrication has made exciting leaps forwards in recent years, for example in spraying of active materials or interactive tools to produce on-skin displays. We have drawn on this work for inspiration and direction in advocating for depositable e-ink display fabrication, using its properties for irregular, deformable display types. In this talk, I'll cover the core contributions of FabricatINK. FabricatINK introduces a novel method to hack damaged e-readers and harvest the e-ink to upcycle it into bespoke displays with a regular shape, as we're otherwise unable to procure e-ink as a material. We use this extracted material to carry out investigations on feasibility of e-ink based personal display fabrication. We also develop a fabrication process for irregularly shaped layered e-ink displays, and using this process we produce key demonstrators to show sample irregularly shaped applications using e-ink. We start by covering the process for extracting e-ink from damaged e-readers. It is not possible for makers or researchers to commercially obtain e-ink as a material. Similarly, e-ink production and microencapsulation is complex and involves significant custom equipment, putting this beyond the reach of all but specialists. So how are we able to work with such a material? We took a direct approach to the problem and we trawled eBay for second-hand devices. We tapped into the market of damaged electronics and bought as many e-readers as we could find in order to attempt to extract the thin film of e-ink that sits inside each one. Using these e-readers, which were typically damaged due to faulty connections but with intact active material, we carried out extensive trial and error testing to develop a way to harvest e-ink and to optimise our yield of the material. Full details of this process for replicability will be made available alongside the publication. But for now, we show the final process. We start with a broken Kindle and we pry apart the solid casing. All components that can be recycled are: we remove the electronics and we carefully remove the battery. We are left with a layered screen structure that we split into 6 parts. These parts are then soaked in acetone to delaminate the structure, allowing us to carefully remove the e-ink layer from the centre. We repeated this process for over 30 Kindles. Using the extracted e-ink, we investigated e-ink to create a picture of its potential through published patents and our own investigations. We carried out a patent review, looking at over 287 US patents. We used those which presented the most information and we reframed them in the context of display fabrication to shape our work. We did this by investigating both the nuanced behaviour of e-ink, but also the potential of what a maker could do with the depositable e-ink beyond an extracted material. Building on our patent review, we then used e-ink to carry out some tests. Here are some real images we took of e-ink within our investigations into the extent to which it behaves as an ink in our fabrication processes. Here we have white and black images of e-ink taken through a microscope, within an e-reader, extracted from the e-reader, and removed from slides and deposited on an alternative substrate. We performed 4 further investigations to shape the fabrication process developed through FabricatINK. We present a 4-stage fabrication process for irregularly shaped e-ink display segments. The shaping of segments, the layering of insulating and then conductive materials, and the attachment of electronics and electrodes. We investigated the damage done through the rupturing of microcapsules as a result of cutting e-ink slides with a range of different cutting techniques resulting in varying damage. We investigated materials and layer thickness of insulating materials to support the e-ink layer structure, ending with multiple layers of acrylic primer applied via airbrush. We also investigated the efficacy of various conductive materials and their tolerances in thickness, ultimately using painted copper paint shown here. Lastly, we investigated e-ink's robustness outside of a hard casing, and found that it has moderate tolerance to pressure. Using the presented fabrication process, we created a series of demonstrations of how fabricated e-ink displays can be applied. We returned to the demonstrators that we created. We produced demonstrations to show e-ink's beneficial properties in different use cases, from wearables to indicators. We also showed further use cases, such as direct integration with paper and household objects, as well as custom touch interactions, with e-ink being addressed by current run over the user's skin. Display fabrication itself opens the doors for decentralized design and production of bespoke displays tailored to their use. Through FabricatINK, we show the material deposition of e-ink as having the potential to be the optimal material for display fabrication, for uses such as e-ink origami, deposition via spraying, interactive nail paint, and digital tattoos, with future work being required to unlock this potential. Thank you for listening to my talk.